Hello and welcome back. In the last video, I talked about stereochemical aspects of nucleophilic substitution reaction. In this video and in the upcoming video, we will be discussing reactions of haloarenes. In this video, we will be discussing nucleophilic substitution, which includes factors for less reactivity for nucleophilic substitution of haloarenes, and then replacement by hydroxyl groups. And these two topics, that is electrophilic substitution reactions and reaction metals, will be covered in the next video. So let's get started. Haloarenes don't undergo nucleophilic substitution reactions easily. So what are the factors that are responsible for this less reactivity? Let's look at them one by one now. I will highlight are extremely less reactive towards nucleophilic substitution reactions due to following reasons. Resonance effect, that is first one. Second is due to the difference in hybridization of carbon atoms in CX bond, instability of phenyl cation, and possible electronic repulsions. Let's look at all of these in great detail now, starting with resonance effect. In haloarenes, the electron pairs on halogen atoms are in conjugation with pi electrons of the ring, and the following resonating structures are possible. So these are the resonating structures that are possible. CCl bond acquires a partial double bond character due to resonance. I have taken chlorine here. In fact, you can take any halogen in place of chlorine. As a result, the bond cleavage in haloarenes is difficult than haloalkane. Next, difference in hybridization of carbon in CX bond. The carbon is sp2 hybridized carbon atom. In haloalkane, the carbon atom attached to halogen is sp3 hybridized, while in case of haloarene, the carbon atom attached to halogen is sp2 hybridized. So this is the haloarene on my left and haloalkane in my right, or in fact left and right of the screen. So in case of haloarenes, the CX bond, the C is sp2 hybridized, while in case of haloalkanes, that C is sp3 hybridized. The sp2 hybridized carbon with a greater S character is more electronegative and can hold the electron pair of CX bond more tightly than sp3 hybridized carbon in haloalkane with less S character. Thus, CCl bond length in haloalkane is 177 picometers, while in haloarene it is 169 picometers. Since it is difficult to break a shorter bond than a longer bond, therefore haloarenes are less reactive than haloalkanes towards nucleophilic substitution reactions. So till now we have seen two important factors. The first one is resonance. Because of resonance, it gets a double bond character and it is difficult to break. And the second one is due to sp2 hybridized carbon atom. So here comes the next one, which is instability of phenyl cation. In case of haloarenes, the phenyl cation formed as a result of self-ionization will not be stabilized by resonance, and hence SN1 mechanism is ruled out. The last factor is possible electronic repulsions. Because of possible electronic repulsions, it is less likely for electron-rich nucleophile to approach electron-rich arenes. So we have completed the list of 4 important factors that are responsible for the less reactivity of haloarenes in nucleophilic substitution reactions. Now let's see replacement by hydroxyl groups, which are in fact nucleophilic substitution reactions but require drastic conditions for the reaction to take place. Chlorobenzene can be converted into phenol by heating in aqueous sodium hydroxide solution at a temperature of 623 Kelvin and a pressure of 300 atm. Drastic conditions, right? So we take chlorobenzene, NaOH 623 Kelvin, 300 atm, followed by acidification, that is H plus, we get phenol. Now let's see what happens if an electron withdrawing group like NO2 is present. The presence of an electron withdrawing group like NO2 at ortho and para positions increases the reactivity of haloarenes. As a result, the conditions have come down. Notice that we have a electron withdrawing group, that is NO2 at para position, and from 623 Kelvin before and 300 atm we just need 443 Kelvin this time. So when we have a para substitution with an electron withdrawing group like NO2 here, and with NaOH 443 Kelvin followed by acidification, we get para-nitrophenol. Now what happens if we increase this NO2, like we have another NO2 group at ortho position. So now we have got an NO2 at ortho position as well as at para position. Now the conditions have come down further. We just need 368 Kelvin this time. So when we take the substrate at the left, which has an ortho and a para substituted nitro group in an haloarene, here the halogen is chlorine to be more specific, and when we treat it with NaOH 368 Kelvin followed by acidification, we get an ortho para substituted phenol. Now what happens if I increase this NO2 group further? What happens if I had another NO2 group at the remaining ortho position? Let's look at it. So now I have added NO2 at 2 ortho positions that are possible and 1 para possible. So all the 3 positions are substituted with an electron withdrawing group, NO2 in this case. Now we just need warm H2O for this reaction. No NaOH, no acidification, just warm water, and you can replace the chlorine with OH. The effect is pronounced when NO2 group is introduced at ortho and para positions. However, no effect on reactivity of haloarenes is observed by the presence of electron withdrawing group at meta position. Can you think why? And that's the next question for you. Can you think why does NO2 group show its effect only at ortho and para positions and not at meta position? I will give you 15 seconds and you can pause the video if you need more time. Okay, let's look at the solution now. So I have removed the question. So this we have a para substituted nitro and attacks takes place, and due to resonance we get another structure like this. Oops, I forgot a nitro group. And yeah, so we have this now. This can again get resonance. We can draw another canonical structure for this, something like this, and we can draw one more. So we have 3 possible canonical structures or resonating structures. So this is equivalent to this structure, and finally thus chlorine is expelled out. You observe that the negative charge is going on the ortho position, then the para position, then on the another ortho position, and then chlorine is expelled out. So what happens if we have the nitro group at meta position? Let's try to draw it. So now I take the nitro at meta position. I again forgot NO2 group, I'm sorry. Yeah, so now we get a similar resonating structures we can draw, like it's pretty much the same thing. By the way, I have skipped the nitro at ortho position. I think you can do it by yourself. It's a similar thing. And yeah, so we get a similar canonical structures and one. Yeah, and finally we have this. Now the negative charge doesn't come under the meta position, and the N in the nitro group is positively charged. Observe that. Let me put it in words. As shown, the presence of nitro group at ortho position and even at para positions withdraws the electron density from the benzene ring and thus facilitates the attack of the nucleophile on haloarene. The carb anion thus formed is stabilized to resonance. The negative charge appeared at ortho and para positions with respect to the halogen substituent is stabilized by NO2 group, while in case of metanitrobenzene, none of the resonating structures bear the negative charge on carbon atom bearing the NO2 group. Therefore, the presence of nitro at meta position does not stabilize the negative charge and no effect on reactivity is observed by the presence of NO2 group at meta position. In simple words, we don't have the negative charge at meta position during resonance, and hence the NO2 group doesn't do anything for stabilizing the negative charge on carb anion. So that is pretty much it for this video. To summarize, we started with reactivity of haloarenes. First, we saw nucleophilic substitution, under which we saw why haloarenes don't undergo nucleophilic substitution easily. We had four factors. And then we saw replacement by hydroxyl group. In the next video, I will be talking about elimination reactions and reaction with metals. I hope the content in this video was pretty clear. Hope to see you in the next video and goodbye.